Hello everybody, I'm Nathan Haltman and Team 3. Joining us today will be Jordan Trotter. Our team has a design problem and today we'll be discussing some solutions that we came up with. The agenda for today is going to be the problem definition and requirements, goal design and criteria. We're going to propose some design and justifications for those designs, and then we'll have a summary and we'll have our references slide. Okay, now I'm going to discuss the problem definition and requirements. We need to have two instruments, one string and one percussion. Each instrument may not exceed $15 in material, and we need to be able to fit 4 of these instruments in a 2 by 2 by 2 cubic box. The design must be aesthetically pleasing, lightweight, and professional quality. Next up, we have our design goals and criteria. Our design goals are the size, obviously, so all the instruments have to fit in the box. We have to keep the cost down to under $15 in material per each instrument. It needs to have good sound quality, it needs to be durable, it has to have a good appearance, and it needs to be lightweight because these instruments are going to be used for travel. Next, we have Jordan Trotter presenting his string design.
Thank you, Nathan, for the introduction. My name is Jordan Trotter. I will be designing the string instrument for this project. Now, the most important feature of my design, as you can see in the sketch of the front view, there is a 30-degree angle cut right here at the headstock, and that's going to help keep the tension back, and that's going to hold the strings in place using the eye bolts as the tuning pegs. And some of the physics involved in my guitar are a cardboard box, which is going to help with sound amplification. Got a 45-degree angle cut down here by the bridge, and by using T-nuts that'll help hold the strings in place. Scale length is actually only 6 inches shorter than a standard guitar, and I will be using bolts as the nut and the bridge. Now, as you can see in the picture, my guitar is only 24 inches long by 8.5 inches wide by 3 inches tall, so it takes up very little space in the box. And it will also cover a very wide frequency range, be using standard guitar strings, so it'll cover the same frequency range as any guitar up to the 4th string down. And this next slide goes over some of the budget and materials I will need to complete my design. As you can see, I did not go over $15. And in order to make this design work, we will need to calculate tension and linear mass density for each string. And by using these data and these equations, I can do that. And this next slide goes over some of the results and specifications for how I will need to design my guitar. And fret placement can also be solved by using this same equation. You just solve for L, and that distance given by L will be the distance from the bridge to the fret. And yeah, that is basically how my design will work. And next we're going to hear from Nathan on how he will design his percussion instrument. Thank you.
Thank you, Jordan, for showing us that string instrument. My name is Nathan. I'll be showing you the percussion instrument for Team 3. What we have here are 8 bars and a sound box which measures 0.6 meters by 0.6 meters by 0.46 meters. It produces notes between A4 and A5, that's 440 hertz to 880 hertz. I'll put up a slide, PowerPoint, so you can take a look at it. The slide also has the budget, which go ahead and take a look at that. Basically all the materials come to $14.15, that's USD. Now let's go into the theory of how the bars work. Here's a mathematical model. And I'll bring up the PowerPoint slide so you can also take a look at that. But basically F equals pi times V velocity times K, which K equals thickness of the bar, divided by 3.46. And then divided by 8L squared times M squared, where V is velocity of the sound bar in meters per second. Oak happens to be right around 3850 meters per second. T is the thickness of the bar in meters. M has to do with the modes of the of the bar, which we'll get into in a little bit. But basically for the first mode, m equals 3.0112. And L is the length of the bar in meters per second. And then what we have here is a graph of this function. So basically as the length gets shorter, the frequency goes up. As the length gets bigger, the frequency goes down. Now let's talk about tuning. Basically the bar vibrates on its two nodal points, which once again I'll bring up another slide so you can take a look at that. The nodal points where the bars are located are simply supported on those nodal points. And then we can tune the bar by removing material in the center, which will lower the fundamental frequency. We can also remove material near the nodes, and that will lower the harmonic frequency. Okay, that was all very interesting. Now let's take a look at a couple other PowerPoint slides. In the decision matrix, I decided to use a simply supported wood design because it's cheaper, lighter, aesthetically pleasing, and it's simpler to machine, thus improving quality. Because wood is cheaper to whittle out those parts in the bar, I can produce a better product because the material is easier to work. Now it's time for our summary. We discussed our problem definition requirements, which were the two instruments. They may not exceed $15 in materials. Four of these instruments must fit in a 2x2x2 cubic box. And also we're concerned about weight and the aesthetics, and also the quality of the sound and the cost. And I hope you enjoyed our designs and justifications.